Okay, so the first is not, what I want to show you, as I mentioned, was how nanomaterials are being looked at today in different ways. And this is a problem that I worked with Steve Sun at Purdue Universities a few years back. It was about the time when water was discovered on the lunar surface as well as Mars, and the idea of in situ recovery of some metals like aluminum. And how could these materials then be used for propulsion applications and for generating hydrogen for power generation. And so the idea came about, suppose I look at the reaction between water and aluminum. If you look at that reaction, overall reaction, I have 2 aluminum reacting with 3 water molecules. It forms aluminum oxide and 3 hydrogen molecules. It's still very exothermic. So it's a source of forming hydrogen. Okay, so it's a way to store hydrogen in a solid form. Okay. The other interest is, if I form hydrogen, it's actually a very good propellant, low molecular weight, and so it's a great fluid to expand through a nozzle. And so the question was, could it actually be used as a propellant? And so what we went through, and we actually mixed nano aluminum with water, and we froze it into ice cubes, and we made basically a composite propellant. And we started to look at its burning characteristics and apply it actually to a sounding rocket and see what could happen. And so what I show here is basically the grain that's formed. This is basically a mixture of nano aluminum and water that's been frozen in a phenolic tube to form a grain. You can actually burn these systems, and if I make a plot then of the burning rate versus pressure, this is the burning rate of the nano aluminum water, and you can see it exceeds many of the propellants that I just showed you earlier, ammonia dinitromen, HMX, RDX, AP, etc. So it has a very fast burning rate. If I were to use micron aluminum particles, it would be very difficult to burn. Okay, basically the surface area is too low and the reaction rates are too low. If you look at the conversion efficiency, nearly 90 to 100% in terms of producing molecular hydrogen. And if you start looking at burning, we actually put it in a sounding rocket, and you find that we did an experiment at Purdue, and you can actually see then, you'll see up here, over here is the launch stand. You'll see very quickly this small sounding rocket eventually take off. It has a very high thrust early on, so it went up. You can't see it anymore, and it basically, the parachute opens and comes back. So it is a successful propellant, not have much use here on Earth because of needing to freeze it, but in terms of other applications of storing hydrogen, one of the applications you can think of, how do we go to Mars? And right now, we're not going to use nuclear power still. We're going to use basically a chemical propellant. But if I want to do that, one of the methods to think about was that people were going to launch a lot of propellant into low Earth orbit and just store it there until I had enough propellant in low Earth orbit that I could bring it all together and start the mission to Mars. If I do that, I can't use cryogenics because the cryogenics won't survive long enough. Okay, but suppose I stored the hydrogen in this form, in a frozen form, until I wanted to make the hydrogen, and then use that to basically use it as a propellant to get to Mars. So you can start thinking of different strategies and using this. Going back to the sintering problem, one of the philosophies in terms of the sintering problem, there's also another problem with small nanoparticles. Because of the high surface area, if I want to mix that into a composite propellant, the surface area being so high makes the prepolymer mix very viscous, and I can no longer stir it. So the amount of loading of aluminum I can add is no longer 15 to 18% before the binder gets so thick that it looks like a dry powder. I can only add maybe 5%. So one of the ideas was, well, suppose I take these small particles and I build them into a micron particle where I preserve the nano features in the interior. And I use an interstitial material that's used as a gasifier. And I can basically choose that interstitial material so I know when it's going to basically gasify. So I choose a temperature that it gasifies when this micron particle, which now can be mixed very easily into the composite propellant, gets near the surface, and then all of a sudden this gasifier basically explodes, and I distribute the nanoparticles in the gas phase above the surface, and I prevent sintering. Well, this is something that's been done at the University of Maryland using basically nitrocellulose as a binder, gasifier material, and nanoparticles. They've used an electrospray technique where there's a solvent. You mix the nitrocellulose in the solvent with the aluminum nanoparticles. You spray it out. You form very small droplets. You let the solvent vaporize out, and what I'm left with then are micron-sized particles that have aluminum nanoparticles in it, plus this gasifier. Okay, and then, as I said, you can vary the gasifier to change basically the temperature at which it gasifies. And the technique's been used to make other types of materials, combinations of nanoaluminum, copper oxide, nanoaluminum and ammonium perchlorate, aluminum and RDX, and other systems as well. But what it basically has showed, if I apply it to a combustion process, if I compare the burning time of these micron particles now with the nanostructure of nanoaluminum embedded in it, I find burning times that are on the order of 40 micron. If I burn just nanoaluminum, which is a much smaller size initially, it's on the order of 400 micron, like 4 milliseconds. So you can see by actually changing the particle from a nano size to a micron size with embedded nano feature, I actually reduce the burning time. And you can see that in these flame experiments here. This is just a burner experiment with methane air in which nanoparticles were added. And you can see the length here is characteristic of the burn time. And here I switch from nanoparticles of pure aluminum to basically micron particles that have this nano feature, and you can see the burn time is much less. It decreases the burn time by a factor of 10 about. And the theory is, as I said, what happens is as I heat up the mesoparticle with the gasifier in it, the gasifier basically distributes the small aggregates, and I preserve then the small features of the nanoparticles. I burn them more like a nanoparticle, and so I shorten the burn time, whereas if I don't have the gasifier, as the particle heats up, they start to sinter, and eventually they'll agglomerate, form a melt, and the particle looks much more like a micron particle that's going to burn longer. People have looked at other types of particles being formed here. This is a typical synthesis reaction for making energetic materials. These are reactive mixed metal nanopowder. So where I take something like a titanium chloride and react it with a lithium aluminum hydride or a lithium boron hydride, I can change the amount of aluminum in the final product or boron by changing the relative amounts here. And what happens is when I combine these together, I eliminate the salt. Basically the chlorine reacts with the hydrogen, and I end up with nanoparticles that basically have a composition of titanium, aluminum, boron. Okay, and these particles basically have a higher energy state within them. They have very little oxygen, no oxygen shell on the surface. And what you find then is their heats of combustion are equal or higher than the nanoaluminum. And if you build in the boron, I have a lower molecular weight. I don't have some of the ignition problems that are typical of boron. And the energetics in terms of performance look very good. And the density, again, is very close to aluminum. So it's another way of starting to look at, instead of just pure particles, looking at combinations of metal particles and using that combination to eliminate an oxide layer and to store energy within the particle. It also has a relatively high hydrogen content, which is useful in terms of the gasification and distributing the particle out of the condensed phase. And I kind of just show that here. These are heats of combustion of looking at titanium by itself, boron by itself, aluminum by itself. The blue lines is what's measured, and if you compare it to these mixed reactive metal powders, you can see the energetics are higher. If you do theoretical calculations to go back and calculate a density ISP as a function of air to fuel ratio or equivalence ratio, you actually find these particles give you an advantage of a few seconds in terms of ISP, which is really significant. Another example of nanomaterial is to use functionalized graphene sheets. You know, you might not think of carbon as being very useful. A functionalized graphene sheet, you know, graphene is basically a sheet of carbon 1 atom thick that might have dimensions of so that's less than a nanometer in thickness, and in the XY dimension, maybe a micron by a micron. So I have a very huge surface area to work with. And if you functionalize it, you can basically put different types of oxides on the surface. And this is an example where just very small quantity of these functionalized graphene sheets was added to nitromethane. And the question was, well, what's it do with regards to the burning rate? And what you see is for less than about 0.4 weight percent, you can almost double the burning rate. So it has an effect. And the question is, well, how's it affecting the burning rate? Well, what's basically happening is at the defect sites where I basically have these functional groups, I'm transferring protons from the gas phase or liquid phase to the functional group on the surface, and it's acting like a catalyst. And that's been shown through molecular dynamics calculations. And if you also vary the amount of active sites on the surface by a reduction process, and you increase the amount of active sites, you can also increase the burning rate as well. What's also been done with the graphene sheets is I can actually pin nanoparticles on the surface at those defect sites. Okay, two examples here. On the left, I use the graphene sheet. It's like a large support system, large surface area, and at each of the defect sites, I put down a nano aluminum particle, and they're spaced all over the surface. And the advantage of this is as the graphene sheet starts heating up, which has a large, high heat conductivity, I no longer can center the particles together because they're pinned at different locations, so I preserve the nano features of the particles. And people have also put nanocatalysts down on the surface, for example, pinning small platinum particles on the surface, and again preserving the nano size of the platinum and preventing them from sintering as well. So it's another way of preventing the particles from sintering up, using the graphene as a support system in a mixture where I now add these sheets to energetic materials. An example of that is in this case where the graphene sheets have been added to, with platinum on the surface, have been added to a hydrocarbon. Okay, the particular application here was if I'm looking at a supersonic aircraft or hypersonic, and I'm going to burn in the combustor at supersonic velocities, I need to, and I want to use a hydrocarbon, how do I accelerate the kinetics? So one of the first things that people have been thinking about is, well, if I have a supersonic vehicle, the vehicle is going to be moving very fast. And as a consequence of that, because of the heat recovery on the surface, I'm going to have a large heat load on the vessel itself. The vessel's going to want to elongate. So somehow I got to cool the vessel. And so people have thought, well, I'm going to use the fuel to absorb that heat. Okay? But the problem is if I use the fuel to absorb the heat, the fuel starts heating up, and I get to a temperature where the fuel starts cracking and I start forming coke, carbon deposit on the surface in the fuel lines. And so that doesn't work. So what people would like to do is they'd like to lower the temperature where the cracking starts before the coke starts to form. And you can do that by adding catalysts to the system. So we looked at adding these graphene sheets with the nanoparticles of platinum on the surface. And you actually see if you add small quantities of these materials, you can actually lower the onset of the cracking process and have a much larger range over which I'm absorbing heat from the surroundings. And so it was added to methyl cyclohexane here, and you can see that more than 20% decomposed with like 0.005 weight percent of the material added to it. So it has a relatively good effect. We also added it to normal decane, and in this case we combined this supercritical flow reactor, which is just a fuel reactor, where the particles were added, and we then injected the products into a supercritical combustor. And you also see an effect of the additive affecting the combustion process as well as the decomposition process and the effective fuel line here. So what this is showing is at various temperatures in this reactor here, if I compare no additive versus just the functionalized graphene sheets by themselves, or if I put the platinum particles on the surface, you can see in the reactor you get more and more decomposition as I add the sheets and the platinum. And the same sort of thing's been predicted by molecular dynamics calculations. And now if I look at what happens when the products come out of this supercritical reactor and I inject it into a combustor, what I actually see is the ignition delays drop significantly and the conversion rates increase drastically as well. So you're affecting not only the fuel pyrolysis and effectively like a fuel line, but you're affecting the combustion process as well. Okay, so this is where I wanted to try to finish. And this is showing now going into more of the pyrotechniques, looking at the effect of these nanoparticles on different types of reactions, thermite reactions and intermetallic reactions. And so people have looked at basically combining nanoscale materials like aluminum, copper oxide, molybdenum oxide, iron oxide at the micron scale and looking at the effect if I drop it down to the nanoscale. Simple experiments have been conducted where basically I have a burn tube. Basically it's a tube where I filled a glass tube that sits inside here with a mixture of nanopowder, and I ignite it at one end and I watch the flame propagate through the tube. There's pressure transducers located along the side here, as well as photodiodes. You can have a high-speed camera and you can watch the propagation rate go through the tube. Typically the way you mix the nanoparticles is you might mix them in a solution of hexane with a sonicator. You let the hexane evaporate out to ensure that you got good mixing between the metal and metal oxide particles. And the reason for doing this, as I mentioned, is really because of energetics. And again, I'm showing here energetics and using TNT as a reference. So if I look at the aluminum copper oxide reaction, looking at the heat of reaction on both a gravimetric as well as a volumetric basis, it again beats TNT. And I can vary that to molybdenum trioxide, nickel oxide, copper oxide, and you can see they're all competitive with TNT. And even if you look at an intermetallic reaction, which is forming the alloy, for example, between aluminum nickel and some other systems boron and titanium, these intermetallic reactions are also energetically competitive with TNT. And so the question is, well, how can I make use of this energetics in this system? If I burn them in that tube, this is the characteristics you see. So what I'm varying here is essentially the equivalence ratio. So, very much like if I varied the equivalence ratio of a methane air flame. This is the lean limit on the left. You see a lean limit, you see a rich limit on the right. And as I go from the lean to rich limit, I see the flame speed increase. Notice I'm going to hundreds to thousands of meters per second. And then as I go on the rich limit, you actually see a change in the burning rate. It drops off through an accelerating front, and then they become very slow. This picture also shows if I change the channel size, that the propagation rate, as I said, is a function of channel size because of heat loss. But it does show if I shrink the channel down, I'm still propagating through channels that are very, very small, and that's because of this very high propagation rate. So the question is, well, why does it propagate so fast? And that's phenomenologically explained here, and it depends on basically the size of the particles and the density, the packing density of the particles. So if the particles are basically packed very loose, what you would typically see in that pressure trace, if I ignite the flame front over here, as the flame front propagates from left to right, you would see basically, because the reaction's so fast with these nanoparticles because of the high surface area between the two, you see a spike in pressure. And that spike in pressure then ends up creating a driving force to drive gas forward. So I create a convective flow into this porous medium, and that convective flow ends up preheating the particles, and that allows then the propagation rate to go faster than a conductive wave. Okay, and that's typically referred to then as a convective wave going through this porous bed. Now, if this was highly packed, the particles were large, then I would see a slower reaction at the front. I would not get a pressure overshoot, and if it was tightly packed, what I would see then, I can't permeate gas through the bed itself, and it would propagate more with a conduction mechanism. So this is more like a deflagration. This ends up being a convective wave, which is typically very important in terms of a transition from a deflagration to a detonation. And that's what's then responsible for those very high speeds. And that's been confirmed if I vary the pressure in the cell. And what it means, if I increase the pressure, you're increasing the pressure in that interstitial spaces. That absorbs heat, and it prevents the overshoot in pressure. So this is a case of looking at the aluminum copper oxide reaction, increasing the pressure in that little tube, and what you see is the very high propagation rates without changing the packing density, and then all of a sudden the propagation rate starts falling off to very low values. And it goes from a convective wave to a conductive wave, and you can see over here, this is the overshoot that is seen. So the pressure overshoot's very large, and then when I get over to the slower propagation rates, there is no overshoot. So it's essentially changing again from a convective to a conductive wave. Okay, so I mentioned the use of self-assembly. And this starts people thinking about how can I start building propellants from the ground up. And what researchers do, they typically look at the non-reactive materials field and they look at how people have been applying self-assembly, supramolecular chemistry to build different types of materials. And this was an example where gold and silver particles were taken, and the gold particles were basically used, and they were ligands were attached to the surface, and the silver particles also had ligands attached to the surface. And what they did is they charged the tail end of the ligands oppositely. So when they joined them together, the particles would actually grow into different type structures. And what you see here is you could actually make structures that look like diamonds and different types of structures that occur naturally in the field. And so the idea was, can this same sort of process be applied to energetic materials? So what we ended up taking was nano aluminum here, nano copper oxide. We took some hydrocarbon ligands, and we functionalized the head end so it had a carboxyl group on it. We attached that to the aluminum oxide. We took another hydrocarbon ligand, which had a thiol group at the head end. We attached that to the copper oxide. And then we functionalized the tail end so that they were oppositely charged. And in a solution, we allowed them to mix together. And what happened was the reaction between the oppositely charged materials basically eliminated the salt, and the particles joined together, and you ended up forming these large micron particles. And in the large micron particles then, I've got nearly perfect mixing now. I've got an aluminum particle adjacent to a copper oxide particle, next to another aluminum particle, next to another copper oxide particle, so I don't have to worry about physical mixing, getting it well mixed. And you end up seeing that the burning process is very fast. I mean, you again get these thousands of meters per second. And so it's a way of starting to think about, how do I assemble these materials from the ground up? Other people have done it, because of time I don't want to spend too much time, but this is a case where nanorods of copper oxide basically were passivated with a polymer layer, and then the polymer layer basically absorbed nano aluminum particles. And again, you can see by getting the close proximity of the oxidizer and the fuel, you can change the burning rate significantly. And it's, again, looking at ways of actually building these materials from the ground up. I mentioned a little bit about putting energetics on chips. Here's an example where I took a silicon wafer, deposited a thin layer of copper, and then I let the copper oxidize, and that forms then these basically copper oxide needles on the surface. And then what I do is I use another chemical or physical vapor deposition process where I just coat the needles with aluminum. So I end up now getting on this silicon wafer basically a nanocomposite system of aluminum and copper oxide that are very tightly knitted, and I can again get very fast propagation rates. And the question then is, how can I use that at very small scale, say on a chip? And people are now looking at, can I use then the energetics from this to basically fire a thermal pile to activate a sensor? Can I use it as a heat source? Can I use it to create heat to basically vaporize a gas? And I'll show you some other examples of that. Another example here is, again, very similar to what I showed you, but using a physical vapor deposition process of creating an intermetallic. This is a aluminum nickel intermetallic where I deposit layers alternately that are nanometers thick of aluminum and nickel. Okay, so now I've made the intermetallic at the nanoscale, and I build up the bulk of that. Okay, and what you see here then are features that look like this. The system actually then will propagate from left to right at very high speeds. Companies are starting to use this actually for soldering. And to show you an example, here's one of the foils that are made. And I'll show a little video here where what they're doing now is they're putting down a little bit of solder. They're going to put down this intermetallic piece here. They'll put down another piece of solder. They're going to put these two metal components together, and they're going to essentially solder them together through a very fast reaction that propagates through the system. People are also now looking at, how can I use it? I mean, in fact, I mentioned, I think, to you the other day, this sort of same process is now used on high definition TVs, where if I got a lot of soldering joints on the back side, I just put a large sheet of this and I propagate a thermal wave through it, and it creates the soldering joints all in one flame propagation. So if you're watching that, you would have seen the reaction propagate through it. Here's another method that's being looked at, using cold spray. Now, you know, this was looking at very fine details. Using cold spray to spray intermetallics to form bulk material. So now in a cold spray system, I have something that looks like this. It's a powder bed system where I feed it into a gas flow, an inert gas flow, and I feed it through a de Laval nozzle. So I accelerate the speed of the particles very high. And then I impact those particles onto a substrate. And I just use the spray gun going back and forth, and I continue to deposit the material like in a zigzag fashion, and I can build up very thick bulk materials that are reactive now. And those materials can actually be machined into different shapes. Okay, you can think of this, suppose I wanted to weld two large pieces. Well, now I just spray an intermetallic on it, I bring the other piece together, and I propagate a flame through it. The Army's actually is looking at this for obviously a military purpose. And the military purpose is, you know, I mentioned to you about the fact that, you know, there's only so much energy I can put into a CHON compound. And that's going to be what's in my munition. But they're now saying, well, how can I increase the overall energy density of this system? Well, one way is to go back and look at the casing itself. The casing's generally inert. And now suppose all of a sudden I change that casing to a reactive material. I've changed the overall energetics of the entire system. And so we've done that. We've actually sprayed up very thick materials. And you can see there's a cylinder here, and you'll see ignited at one end, and it's propagating through the system. Now, something like aluminum nickel is not obviously good for the military use that I talked about because it doesn't have enough strength in it. But other metals, some of those other compounds that I showed you do. There's other methods. You know, I've been showing you sort of bottom-up approaches. People have used top-down approaches of actually making materials. This is a typical milling process that's referred to as a arrested reactive milling. I start off with micron particles. I mix them together, and I ball mill them. And I ball mill them long enough such that I start creating particles with nano features of one component in another component. It's referred to as arrested because as I ball mill it, this is a reactive component. And so the temperature is going to start rising. And I don't want to reach the temperature where it auto-ignites. So what I do is I'll ball mill it for a certain amount of time. I let it cool off. I ball mill it a little bit more until I get the desired microstructure I want in the particles at the end. And because this is such an easy technique, it's used to all different types of metal compounds, thermites, intermetallics, and they've been integrated in energetic materials. Again, embedding catalysts inside ammonium perchlorate particles, or instead of using, again, using ball milling processes, not with a metal and a metal oxide, but with basically a fluoropolymer and a metal. Okay, to create, again, components with different types of characteristic and features. I mentioned also that, you could also make small nanoparticles of oxidizers. It's been done with basically supercritical processing, where I basically take the oxidizer, dissolve it in a supercritical fluid like CO2. You get enough absorbed in it. You expand it through a nozzle, and you just let the small particles start to nucleate, and you stop the nucleation process at the diameter particles you want by basically shooting it in a liquid or something like that. And people have made then nanoparticles of RDX, and again, they're very reactive. Talking about nanoparticles, probably, the ultimate is to go to making clusters of the metal particles. And there was a person in Germany by the name of Schnockel, and now it's referred to as a Schnockel reactor, where basically he's shown you can actually build up clusters of aluminum in shells. So I start off with a shell here that has 13 atoms embedded around it. I have another shell with 44 atoms embedded around that. I have another shell of 20 atoms, and I end up then with an aluminum 77. So it's a very small cluster that's going to be at very small length scales, very reactive. And what you do then is at the outer shell here, you basically passivate these atoms with a ligand. And I've got a very small reactive metallic content, and if I can control the dynamics and the ligands there, I'm going to have a very fast burning process. The other interesting feature about this, Will Castleman at Penn State has actually been studying these clusters for years, and he actually finds that you can actually change the chemistry significantly by adding one atom at a time to the cluster. So if I have a cluster aluminum 12 and I add one atom, I go to aluminum 13. The aluminum 12 is really reactive with oxygen. I go to aluminum 13, it doesn't react with oxygen at all. And what you end up seeing, and what he's kind of proposed is, as I make these clusters, it's sort of like a third dimension of the periodic table. And so the ability to start fabricating these clusters and control their size, you can also change their chemical reactivity. And so there has been some studies in terms of putting this in energetic materials. This is some work, again, that's been done at University of Maryland, making basically an aluminum fluoride cluster with basically a bromine ethylene passivating material around the outside. So you can see basically the aluminum fluoride cluster here and the passivating ligands. They've put this in solution in hydrocarbon droplets, and what they find is by putting it in a hydrocarbon droplet, you actually change the burning rate of the hydrocarbon droplet. You actually get condensed phase reactions with the cluster that accelerates the decomposition process of the system. Okay, I don't want to, let me just say that, silicon's a fuel as well as aluminum. And, when I was talking about, putting energetics on chip, people have looked at using silicon, and what they do then is, like if I want to put it on a chip, what you can do is basically perform an electrochemical etch to create pores inside the silicon wafer. And these pores can be on the order of 2 to 10 nanometers thick, depending on the etch that you do. And then you can fill those pores with an oxidizer, and I end up forming a composite propellant then. And so if I'm making a chip, I can locally just make the pores at some local region on the chip and fill those pores, and I can have that end up doing different functions. And the reactivity in these systems is quite high. Silicon's of interest because it has a lesser oxide layer. The functionality in terms of putting functional groups on the surface is much better known from a chemical point of view. You can attach fluorocarbons to the surface, and so that the type of chemistry you can actually work with is much, much greater than with aluminum. And so just to give you an example of what's been done, people have etched on silicon wafers just regions like a strip here of porous silicon. They've filled the pores, they've deposited a copper electrodes on the surface, they ignite it, and they measure the propagation down the system here. And you can find, again, very high propagation speeds on the order of thousands of meters per second. And it basically can depend on the etch depth as well as basically the pore size. And it looks like the optimum pore size is about 3 nanometers. And if you ignite it at the end, you can see it propagating down as I show you here. What this also offers is actually using MEMS techniques. Now I can start masking certain regions and putting these energetic materials in different ways. I can also start creating different sort of structures on the surface as well. And this is an example of that. Here's a cartoon image of a piece of silicon wafer. And what I've done is I've created a mask at this top surface where I actually create pillars that have dimensions of 8 micron by 8 micron. And then what I do is I do the chemical etch on top of everything. And so on this region down here, I created the nanopores that were maybe 2 nanometers in size. On the pillars, I also have now 2 nanometer pores. But notice in this region, I have just one dimension I'm dealing with. In this dimension, I'm dealing with 2 dimensions, the pore dimension as well as the pillar dimension. Look what happens when I propagate the flame starting at this point upwards. And what you're going to see is basically the side view of the gas coming off the surface. So you're not looking top down, you're looking at sort of 90 degrees here. And so now the flame's propagating up, the gas is coming off. This is still moving rather fast, probably, a few, 36 meters per second. So, compared to a flame speed. And now it's getting to the region where the multi-scale is. You change the reaction rate by orders of magnitude. Okay, and that's again, changing the propagation mechanism. Down here, the reaction was propagating through a conduction mechanism. Up here, I transitioned it into a convective mechanism. You can create shock fronts off the surface. I'm going to try to move on a little bit faster here so we can end. But if you're looking at the side here, the gas is coming off the surface so fast, it actually creates a shock front in the gas phase. And so one of the questions is it this shock front that's moving along with the reaction that's assisting the reaction front as I go? And in this case here, there was a piece of this porous silicon, and there was a location where the porous silicon, the oxidizer, wasn't filled. And so as the reaction was propagating front, there's a shock front here, there's the reaction, and you can see when the oxidizer is not present, the shock separates from the reaction. And when the shock got to the other side where the oxidizer was again, it reignited the mixture and propagated along. But if you go through this and look at some experiments that would try to understand whether or not the shock front is the reason for the high speeds, you end up finding that it's not. Okay, the shock front is just present there. It looks like a piston being moved off the surface and just creates a very, as a result of the very high velocity. So let me just, there's a few slides here and I'll finish then. You know, I want to just show you some examples of how now these nanoenergetics is being incorporated in different types of systems. They're used for microthrusters, microactuators, micropumps, a whole host of applications. And again, it comes back due to the energetics at the small scale. So if I start comparing the energetics of an energetic material or something like a nanoporous system, you can look at the energy density and compare it to other means of storing energy, through piezoelectrics, electrostatics, electromagnetics, and by far the energetic material exceeds that. And so here's some examples of starting to look at on-chip integration, where locally on a chip I'll create a porous region maybe, and in that porous region I'll deposit and I'll want to create a reaction there for some reason. And it could have different applications. It could be for on-off switches, actuators, igniters, thrusters, surface deflection. And here was just a sample. The width of this channel here, these little channels going around, is on the order of about 25 micrometer. And you can see if I ignite it, the reaction, it propagates, which is normally constant, but it propagates through this system very fast. One of the first examples was something that TRW did, made microthrusters through a MEMS process, where they use silicon wafers that create nozzles and diaphragms on the surface. They use basically a glass combustion chamber that they filled with an energetic material, and on the other side of the silicon wafer they deposited polysilicon resistors so they could use it as igniters. And this was actually flown on the shuttle to look at basically using these small thrusters that could be built up in arrays to produce thrust on very small satellites. And the idea was, instead of having a single rocket motor, if they wanted to directionally position the thrust, they could fire multiple of these digital thrusters at once. Making little robots. Suppose I wanted to put a sensor out in the field, and I wanted this sensor to stay out in the field for years. And I knew an electrochemical battery is not going to be sufficient because it may stay there so long that the energy would decay out of the battery. Well, I basically put an energetic material on this little chip, and I'm going to use that to fire up. And so what's used in this particular case is a phototransistor. When it's hit with a beam of light, maybe there's a flash from an explosion or something, that basically fires this resistor down here. It ignites this porous silicon with an energetic material in it, and it ends up making this robot hop high enough that some of the energy is then put over to a capacitor. This capacitor then fires a sensor, and when it's in the air, I have an active sensor to do something. So you can see the multi-applications of actually embedding energetics on chips. This is another example where in a MEMS safe arm fire system, the energetics is doing multiple activities. There's a little bit of energetic material put down here that basically creates a switch. It melts a soldering joint that opens or closes a switch. Then that fires over here a gasifying energetic material that produces gases that moves this arm over to align this hole here. And this is an energetic material then that fires, and it is used as an igniter to set off basically a larger system. So, I think to summarize, where the field needs work and where we are is sort of what I talked about at the end of the day yesterday with regards to scientific issues. You know, we really don't understand a lot of the more complex processes that occur at very high pressures in the condensed phase reactions, the dependence of the burning rate on pressure, surface phenomena. So there's a number of issues that, you know, a lot of help, a lot of good thinking could apply to. Experimental challenges with these materials, you know, we're dealing with very small length scales, very complicated three-dimensional structures. Diagnostics don't work very well at high pressures. So, you know, there's a need for potentially developing new diagnostics and how can one, you know, interpret material and characteristics in the condensed phase. Looking at the types of needed measurements, burning rate, flame temperatures, anything really to describe the microstructure, what's happening, you know, in the condensed phase material. There are some experimental techniques that are being developed in, you know, different types of digital holography, high-speed pyrometry, and these are, you know, moving slowly, but, you know, there's potential for better applications and understanding of the material. There's also numerical challenges. These come about mainly because of the multi-scales in the problem. I'm dealing from, you know, nanoscales all the way up to the micron scale, to the millimeter scale, to the centimeter scale. And how does one deal with that multi-scale type simulation efficiently? I think I said most of that here. Development of energetic materials itself, you know, looking at organized nanomaterials. How do I develop smart materials versus looking at trying to put more energy into the system? The use of metal clusters, and now really looking at additive manufacturing. Industry as well as universities are now heavily involved in looking at different types of additive manufacturing, inkjet, to basically build all different forms of energetic materials. And you can imagine now, suppose I wanted to build a composite propellant and I wanted it to burn slow in the beginning and then all of a sudden fast later on. So if I could spray this and deposit this material, I could have very fine length scales when I wanted it to burn fast, and when I wanted it to burn slow, I increase the length scales. And as a consequence of that, I can actually tune the burning process for a particular type of application. So I think, you know, the directions forward are to basically, you know, start concentrating on making these materials more smart. Can I use external fields to start altering the reaction rates, the reaction propagation mechanisms, change a material from being sensitive to less sensitive, change a material while it's propagating, say, from a deflagration, and then all of a sudden igniting the rest of the material to homogeneous ignition, and looking at really new applications of the materials itself. So, you know, a little bit over time, but, you know, I tried to cover probably a little bit too much, but I wanted to give you, you know, sort of an overview of, you know, starting from simple basics and where really the field is today. And if you look at as I said, if you look at the appendices, I put a whole list of references there that are really useful to look at if you're interested in this area to read. And then there's some other appendices that I take some of this material and actually relate it to applications of rocket motors and looking at how, if you change some of the characteristics, how it affects a specific impulse, thrust, and different characteristics that would be important in terms of metrics and motors. So if you have any questions, you know, you can come up and ask me. I'm willing to stick around and talk, but thank you very much.